this video, I'm going to talk about Chapter 32, Sections 4 through 7. And these are going to deal with what happens to light when it's traveling through a medium. We know that in a vacuum, all light travels at c. Okay. But light travels slower when it travels into things like glass, water, quartz, diamonds, and we assign a number to those different materials called the index of refraction. The index of refraction is defined to be a number n, which is equal to c over v. N will not have any units. We know that c is the speed of light in a vacuum, and v is the speed in the material. For example, we know that v is equal to 2.25 times 10 to the 8th meters per second in water. Say, light always travels slower when it moves into a medium, so the index of refraction for water is going to come out to be 1.33. The index of refraction is always going to be a number greater than 1, and that's because c is the fastest speed of anything. In any substance, it will travel slower. The index of refraction for air is about 1. In other words, when light travels through air, this speed is very, very, very close to 3 times 10 to the 8th meters per second. It does not appreciably slow down. And that pretty much concludes Section 4 out of Chapter 32. Section 32-5 deals with Snell's law. Or you could, sometimes this might be called the law of refraction. We know that when light is incident on a medium, two things happen. So here's a boundary between two mediums. And when light is incident on that medium, here's our normal segment. If I have a beam of light, comes in like this, that's the incident ray. Part of that light is going to be reflected. But part of that light is going to be transmitted. And when it does, it's going to bend. It might bend closer to the normal, the way I've drawn it here, or it could bend farther from the normal. This is our refracted. And it depends on the index of refraction. If light slows down, it refracts towards the normal. Well, if it slows down, that means that this index of refraction is greater than this index. So if I call this N1 and I call this N2, if N2 is greater than N1, light slows and it refracts toward the normal. If I I had a different situation and I had light traveling from, say, a higher index into a lower index, let's just draw another picture altogether. Again, if we have an incident ray, part of that ray is normally reflected and part is refracted. Notice this time I drew this refracted angle much larger than the incident angle. That tells me, in this case where this is N1, this is N2, that the second index of refraction is less than the first index of refraction. In that case, the light actually speeds up and we will refract or bend away from the normal. So I want you to understand how the light behaves. When it slows down, it bends towards the normal. When it speeds up, it refracts or bends away from the normal. To actually calculate these angles, it's really easy, and it's done using Snell's law. Snell's law says N1 sine theta 1 equals N2 sine theta 2. Like I say, that's Snell's law. It's sometimes called the law of refraction. Let's work a quick example. In this example, we have a piece of flat glass. Here's a piece of glass. This has an index, this is air over here, and the index is 1. The glass here in the middle has N equal 1.50, and then back into air, N equal 1. It asks a question, it wants us to find the angle inside the glass and the angle as the ray leaves again. So what's going to happen, it says we start with an incident ray. It's coming in at 60 degrees. I may not have drawn that perfectly. It will bend toward the normal. It will slow down, so it's going to bend and go across the glass. And then there's our second normal. So this is, I'm going to call that angle A. And then when it leaves, since it will speed back up, it will refract away from the normal. I'll call that theta B. The problem would like us to find the angle in the glass and then the angle at which the ray actually leaves the glass. So we're going to start going from here to here. So initially we'll call this N1, we'll call this N2. And so we are going to have 1 sine 60 equals 1.5 sine theta A, because I called it theta A in the picture. If I type in my calculator 1 sine 60, this is 0.577 equals 1.5 sine theta A. Whoops, I already divided by 1 point. This just equals sine theta A. Already done all that. So to get the actual value of the angle, I have to do a sine inverse. And I get that that angle is 35.3 degrees. That agrees with my understanding that that angle should be smaller. I should bend toward the normal. So that's part A. The second part says, okay, well, what's theta B? Well, if this is theta A, if this is 35, then you know what? That's theta A also. Those two are what we call alternate interior angles. Those who remember your geometry. So let's just go from A to B. So if you want, you could even think of this as 3 into sine theta 2. So 1.50 sine 35.3 equals 1 sine theta B. If we solve this, we're going to get something 0.866 equals sine theta B. And theta B comes out to be 60 degrees. If you think about it, that makes perfect sense. So, although we get shifted a little bit, we are still on the same angle when we come out. Section 32.6 deals with the idea of dispersion. You'll remember that when we talked about the electromagnetic spectrum, it covered a broad range of types of waves, everything from radio waves to gamma rays. The smallest part of that spectrum is what we call the visible spectrum. Those are the wavelengths and frequencies that our eyes, the rods and cones on our retina can actually detect. They range from 400, the visible spectrum. The light we can see ranges from 400 nanometers. That's violet light, to 750 nanometers, which is red. If you have wavelengths that are slightly less than 400, slightly shorter, right next to violet, we have what we call ultraviolet or UV. If we let the wavelength get just a little bit longer than 750 nanometers, we are right next to red. We call that infrared radiation. These three types of radiation are what we get from sunlight. Infrared is detected as heat. Of course, visible spectrum is that part we can see. And UV, we don't sense, but we get a lot of it. And it's responsible for skin damage, premature aging, skin cancer. So that's one of the reasons we want to protect our skin when we're outside. Use that SPF 50. One of the things we know is that although light travels at the same speed in a vacuum, all light, gamma rays, radio waves, it doesn't matter. When light travels through different materials, different wavelengths travel at slightly different speeds. So red light actually travels a little bit faster than violet light. Violet light has a slightly higher index of refraction. The result of that they travel at slightly different speeds, is that when you send white light through a prism, here comes some white light, and it refracts towards the normal, and then it refracts away from the normal. What you see coming out, instead of just, because they each bend slightly different, is a rainbow of colors Violet will bend the most. Let's see if I can track this through. It will be becoming more violet coming in here. Slightly larger angle here, so even larger. I think I drew this right, and maybe backwards, but I think I drew that right. So we're going to get all the colors from red to violet: red, orange, yellow, green, blue, violet, and it's going to look like a rainbow. That separation of colors, because of those slightly different indices of refraction or the slightly different speed that the light travels, is called dispersion. Another example of dispersion you're probably familiar with is a rainbow. If the sun is at your back and there are water droplets ahead of you, those water droplets act like little bitty prisms, and the result is you see a rainbow. Okay. Another result that we need to stop and think about is we know that, let me just erase all of this for a minute. We know that V is equal to wavelength times the frequency. When light travels into a new medium, this does not change. F does not change in a new medium. So if you have red light that has a frequency of 7.5 times 10 to the 14th hertz, and that red light travels into water, it still has a frequency of 7.5 times 10 to the 14th hertz. Its frequency won't change. However, it will go slower. It goes slower by a factor of n. Well, if it travels more slowly by a factor of n, the wavelength also has to be reduced by a factor of n. So we know that the velocity is c over n in this new medium, and the wavelength is lambda 0 over n, where this is in a vacuum. As soon as it travels into a new medium, it slows down, and the result is a different wavelength. So if you think of this as being air and this being glass, and we have a wave that's traveling like this, when it comes to the glass, it has to go slower. Its frequency doesn't change, but it slows down, and the result is the wavelength is shorter by a factor of n. So this would be something like air, water. That's an important idea to remember. We already know this first one is true, but we also need to remember that since it does slow down, it also changes wavelength. Our last section, I can't believe we've already made it to the last section, 32.7 deals with something called total internal reflection. All right, we know that when light changes mediums, it can refract toward or away from the normal. Total internal reflection can only occur when something's in something with a high density and it's trying to get into material with a lower density. So for example, suppose I have air here and I have some type of glass down here. have a ray that's coming in. Here's theta I. That's my incident ray. When it hits this glass, generally speaking, part of the ray will reflect back in, and I'm going to draw the reflected back in, but part of the ray will refract away from the normal. So this is incident, and this is refracted. Well, if I take that ray, I should have used a different color, and I increase the incident angle. I make the incident angle even greater. So it's coming in here, incident. When it refracts away from the normal, at some point, that refracted angle would increase all the way to 90 degrees. This is called the critical angle. If you try to come at an angle that's greater than the critical angle, you will get complete reflection and no refraction. So, anytime you have an incident angle greater than the critical angle, you get 100% reflection. None of the light can escape. What's that look like in terms of math? Well, N1 sine theta critical. And I want to point out here that in order to have this, N1 must be greater than N2. You must be in a higher index material trying to go into a lower index material, or a slow material into a fast. Has to equal N2 sine 90. The critical angle is the angle at which the refraction would be 90 degrees. Anything bigger than the critical angle, and you plug it in, and you're going to get an error in your calculator because you can't have an angle, you can't take a sign of a number greater than 1. You can't have a refracted angle more than 90 degrees. So it looks like this. If this material happens to be air, and it often is, that would be 1. Sine 90 is always 1. So we end up with a situation where sine theta critical equals, since sine 90 is 1, N2 over N1. So, for example, if N2 is air and N1 was a diamond, I did not have that right, which is about 2.42, this is air, we can solve for the critical angle. Sine theta critical equals 1 over 2.42. We just have to do a sine inverse. When we do, we find out the critical angle for a diamond is about 24.4 degrees. What's that mean? Well, suppose that this is air. Here's your diamond. Here's a normal. Anytime, 24 degrees is only about this far. This is theta critical. Anytime you have a beam of light that is incident at an angle more than the critical angle, it's outside here, it completely reflects back inside. This ray completely reflects back inside. The only way to escape is to come in at an angle that is less than theta critical. I'm going to let this red light be at a different one. It's less than the critical angle, then it can get out. The smaller the critical angle is, the harder it is for light to escape. The reason that diamonds are so sparkly is really two things. Part of it's dispersion. When white light enters a diamond, it separates the colors like a prism. But the other part is diamonds are cut in such a way, and diamonds cuts look sometimes something like this, so that when light comes in, and this is by no means a measure, it tends to do things like here comes some light, and it bounces, and it bounces, and it bounces, and it bounces, and it finally gets out. It finally comes at it, but it bounces around. So the light literally spends more time in the diamond. So between separating all the colors, because it acts like a prism, and the fact that a light ray will bounce around several times before escaping, makes diamonds sparkly. Glass has an index of refraction of about 1.5, 1.6. It won't have the same effect. It'll have a little bit of that sparkly effect, but not nearly as dramatic. One of the primary uses of this, much more practical than making jewelry that sparkles, are fiber optics. Fiber optic cables, and I don't have any fiber optic cables here at the house, but they're essentially flexible plastic cables. And this is gigantically enhanced. What makes them so nice is you can run them through buildings, you can run them under the oceans, they're easy to work with, and yet they will allow telecommunications, data communications, all this new digital information to be transmitted with almost no loss because of total internal reflection. A beam goes in, it bounces, it bounces, it bounces, it bounces. Regardless of how you bend this, these fiber optics have an index of refraction such that you don't get any light out till it comes out at the very end. If you've been to the circus or the zoo, they sell those little toys that have all the little plastic things hooked up on a flashlight. And you'll notice the light comes out at the very end of each of those little plastic, I don't know what to call them. They're not exactly wires, little plastic filament things. They look like little pieces of fishing line almost, with light coming out at the end. That's total internal reflection. All right, this concludes chapter 32. This concludes physics 24, 26. Good luck, and I'll be in touch.